We've talked about integers, which can hold whole numbers. But what if you want to store a fractional number in your sketch, like 1.5 or minus 2.5? You can't put those numbers into an int because they have a fractional part, and ints can only hold whole numbers. So there's another type of variable that lets us hold these kinds of numbers. It could have gone by a lot of different names, but the name we use is float. This name comes from another name. When programming, numbers with fractional parts are called floating point numbers. That's because in this kind of number, you can put the decimal point anywhere you need it to go. For example, suppose your number is 1.234. Then the decimal point is between the 1 and the 2. Now suppose your number is 12.34. Here, the decimal point is between the 2 and the 3. We still have the same 4 digits, 1, 2, 3, 4, but the decimal point is in a different place, and of course that means we have different numbers. Because the decimal point can go anywhere you need it to go in a fractional number, people thought of the decimal point as being able to float or move anywhere you need it to go. This idea might be a little metaphorical, but the idea stuck, and we now call these floating point numbers. Rather than type out the whole phrase floating point for every variable, we just abbreviate it to the word float. A variable of type float can hold any kind of number. It can hold whole numbers, like the integers, and fractional numbers, like 2.5. It can hold positive numbers and negative numbers. To see this in action, let's create a few floating point numbers. I'm going to write a little program that imagines we have a plate of cookies, and we want to know how much all the cookies weigh. So I'll make two variables. The first tells us how much each cookie weighs. For this discussion, I'll assume that each cookie weighs the same thing, 1.3 ounces. Because this number has a fractional part, I'll make its variable a float. The other variable holds the number of cookies. Now, suppose we have 8 cookies. This is a whole number, so I'll store it in an int. The total weight is found by adding up the weight of each cookie. Because they all weigh the same, we can just multiply the cookie's weight by the number of cookies. Since this might have a fractional part, I'll make this variable a float. Then I'll print out the results. So let's run this and find out how much our plate of 8 cookies weighs. The total weight of our cookies is 10.4 ounces. That's a fractional number, so it's a good thing we used a float. Now suppose someone eats half of a cookie. We now need to change the value of number of cookies to reflect that, reducing it from 8 to 7.5. Let's try to run this. The program won't even get started. We get an error right away. The assignment statement is highlighted in yellow, and the error message says, "Cannot convert from float to int." Well, that makes sense. We're trying to take the number 7.5, which is a float, and stick it into number of cookies, which is an int. And as we know, integer variables just can't hold floating point numbers. So no problem, I'll just change number of cookies to be a float. Now we can run this program successfully, and we find that the total weight of our 7.5 cookies is 9.75 ounces. And that's right, it's our previous total minus the weight of half of one cookie. That's really all there is to floats. We can put any number we like into a float, positive numbers or negative ones. We can even store integers, like 2.0. So if a float can hold whole numbers, like 2.0, why even bother with ints? Why not make everything a float all the time? Well, if you're willing to work hard enough, you certainly could. But we have both ints and floats around because the ints are very convenient for two kinds of things we do all the time: counting and comparing. So let's look at counting first. Suppose we're trying to fall asleep, and we try that old trick of counting sheep. Then we count them with the counting numbers, 1, 2, 3, 4, and so on. Now we never have a fractional number of sheep. We should never have 4.7 sheep, just the whole numbers. If we were writing a program to count sheep, and we used a float for the number of sheep, we could have a bug in our program that accidentally tried to record 4.7 sheep. And that would work, because we can put 4.7 into a float. Suppose instead we protected ourselves. We declared our variable to be an int. So now if we tried to put 4.7 into that variable, processing would stop and tell us we have an error. Well, that's great information because it will help us track down and fix the problem. So by declaring a variable to be an int, we can make sure it always holds a whole number. And if we ever accidentally try to put a fractional number into it, we will get notified. Well, that is a fabulous safety net, and that's one of the great advantages of having different kinds of variables. It's kind of like putting handrails on stairs. You don't absolutely need handrails to make a flight of stairs, but the stairs get a lot riskier if you don't have them. Having no handrails can lead to really scary flights of stairs. Having the handrails helps a lot. It's kind of a safety net to protect us from making slips. Another reason for using ints rather than floats comes up in the very frequent task of comparing numbers. When we ask the computer if two numbers are the same, usually we're asking for an exact match. And floats have a problem with that because they're not always that precise. Think about your bathroom scale. This doesn't give you an exact weight down to a dozen decimal points. Your scale is probably accurate to within a pound or two either way. Floating point numbers can be that way too. When we store a relatively small number, like say 200.0, typically that number is stored as just that, 200.0. Here I'll stick 200.0 into a float, print it out. Sure enough, it's 200.0. Suppose now that we just make this a little more interesting. I'll take f and divide it by 3, and then multiply it by 7.5. Okay, now f has some crazy value, but now I'll undo the operations, and I'll multiply it by 3 and divide it by 7.5. Now f should be 200.0, just like where we started. So let's try it. And this is not 200.0. It's very, very close, but it's not exactly right. Generally speaking, you will never care about this tiny, tiny little bit of inaccuracy. This number is so close to 200.0, you'll never notice the difference. But the computer does. If we ask the computer, is the value of f the same as 200, the computer would say no. It doesn't really have any idea of a number being close, but not exact. To processing, if we ask, is this number 200.0, it will simply say it is not. Close doesn't matter. We'll see later that testing a number like this is something we do all the time. For example, we might ask our user to type in their phone number. That should have 10 digits, not 9.999 digits or 10.001 digits. If we store the number of digits in an int, then it's easy to test because it's never a little bit high or a little bit low. If we save 10, it's always going to be exactly 10. The general rule is this. If you're ever creating a variable that you know should never have a floating point value in it, then protect yourself and use an int. On the other hand, if you're storing a variable that may have a floating point value, use a float.